Well, good morning. My name is Iria. I'm a first year PhD student at the Barcelona Supercomputing Center in the Computational Biology group. And today I'm going to talk about one of the projects that I'm working on, that is Unraveling patient heterogeneity through explainable AI and network-based strategies. Well, so complex disease present diverse molecular profiles and have various underlying causes, making it challenging to identify biomarkers associated with the disease progression and to develop effective personalized therapies. This is the case of many cancers, autism or epilepsy disorders, and also of chronic obstructive pulmonary disease. COPD is an heterogeneous condition that is characterized by the level of airflow limitation, and it can be divided into 4 levels of severity: mild, moderate, severe, and very severe. It has smoking exposure as the first risk factor, but difficulties while detecting COPD make the diagnosis appear um, with more severe obstruction profiles, leading to a need for develop strategies for an early detection of the disease. Moreover, previous studies show little overlap among its molecular biomarkers. So here, what we propose is to, focusing on COPD, construct a comprehensive framework for characterizing and standardizing complex disease. So our approach has 3 key components that are a feature selection, a prediction performance, and then a sharp value analysis. So in our project, we use gene expression coming from 2 microarray platforms that were substituted to a group of first processing steps that are background correction, normalization, filtering of lowly expressed genes, and low quality samples. So we ended up with a data set of 300 samples on more than 16,000 genes. So this is the data that we will be working on for this talk. So the first step of our approach was to divide the dataset into training and test set, and then, given the last number of genes in our data, we apply several filtering approaches in order to extract the genes that are more relevant for the classification, but also avoid adding noise that could deteriorate the classification. So our selection criteria has 3 different approaches. The first one is the data-driven one that basically combines the differential expression analysis with a minimum redundancy, maximum relevance algorithm that selects those features that are relevant for distinguish between 2 categories, but also select those features that are less redundancy with the previous selected ones. Then we wanted to complement our approach, extracting information from other sources. So specifically, we wanted to extract information that was directly associated with the disease. So for that, we use this GeneNet, that is a database that has genes associated with a specific disease. However, the overlap between these 2 approaches, the data-driven one and the disease-related one, was poor. So we decided to expand these 2 lists of genes using, on one hand, Gildify, that is an algorithm that prioritizes genes based on biological data integration and network-based prioritization algorithms. And on the other hand, we use OmniPath that basically select the first interaction genes. So this is the basis of our first step of the framework. And then the second step was the prediction performance. So what we did was to use this 9 list of genes as input to our classifiers. And we trained the models using a cross-validation performance, and each model has also its own internal machine learning preprocessing, for example, downsample to correct the unbalanced number of samples between conditions, or trying to make the features more symmetric. Then what we did was to make an hyperparameter tuning, and then we train the models that are a random forest model, a support vector machines with both radial and kernel and polynomial kernels, a generalized linear model, an XGBoost, and a K nearest neighbor. Then what we did was to evaluate our models using the Matthews correlation coefficient and comparing both the test and the cross-validation results. So with this, we have the second step of our framework, and then what we have here are the results of our classifiers. You can see the different machine learning algorithms in the vertex of these radar plots, that are colored by the different genes of list used. And we are showing the normalized Matthews correlation coefficient. So the first thing that we can see is that the disease-related genes are the ones that have the less Matthews correlation coefficient value in both cross-validation and test sets, and also that the data-drivens are the ones that achieve the highest accuracies, the highest performances in 4 out of the 6 classifiers in the cross-validation and in 2 out of the 6 classifiers in the test set. In fact, the KNN using the data-driven genes is the one that achieves the highest accuracy in the cross-validation and the second highest accuracy in the test set. So what we did was to compute the SHAP values for this model. So here, what we have in the heat map are the SHAP values for the top 50 genes with higher aggregated SHAP values. In the upper bars, we have the disease condition that is in blue for COPD and in pink for control samples, and also the gold stages. Well, basically, we can see that the SHAP values allows us to effectively distinguish between controls and COPD patients. And also in the bar plot, what we have are the top 10 genes for each gold stage level, and with higher SHAP values. And we can see that there are genes that are common for different gold stages, and are others that are exclusive of one gold level. So there are different gold stages that have unique discriminant genes, and also some of the genes, in fact, those involved have been previously linked with COPD. So with this, I ended up the framework that we proposed, that this has the 3 steps: the feature selection, the prediction performance, and the SHAP values. So what's next? Well, this is an ongoing project. We are still working in the SHAP value analysis. These are preliminary results. So we wanted to analyze them further. And also we are performing a multi-class classification, taking into account the different gold stages of the disease, and also the molecular, the underlying molecular characteristics. And we also would like to validate our methodology in other heterogeneous diseases, such as breast cancer. So thank you so much. Thank you also to my group, and hope you have enjoyed it. And if you have any questions, I would be glad to answer it.
Do you have any questions over here? I think I can take it to you.
Oh, that's good. I think I've got a quick question. Oh, yeah, okay. So that's great. So thank you. So you have 2 microarray data sets.
Yeah.
I was wondering, were the conditions split between the 2 data sets?
No.
Okay.
Both data sets have 2 conditions. One has like 60 patients, and the other, the rest, 1,040, something like that.
Right, thank you.
Very nice talk. Thank you. I was interested in talks like this when there's a benchmarking of a lot of different machine learning approaches, and very often, or sometimes it happens that the simplest approach is the one that is the best for you. That is the case as well. The k-nearest number is one of the simplest algorithms for any type of this classification of this type. Do you have an idea why that is the case? And have you tried anything deeper, some like deep neural networks? What would be your approach in this specific application?
Yeah. Well, it's surprising for me also that that's happened. I tried a basic deep learning model without any complicated topology. But what happened is that I have very low samples, so it tends to overfit in, and the cross-validation results or the results of the training are so good. But then if you try it in the test set that you let alone of the analysis, the results are so bad. So I would like to do more complicated models, but for that we are collecting more data, so we have to wait for that. Yeah, I don't have an answer for why the KNN is the best one, but in fact, the point here is that any of the classifiers is much better than the other ones. It depends a lot of the genes that you are using, and also on the classifier itself. So yeah, what we see clear is that the data driven is the nicer approach, but we would like to find also other genes that are not easily recovered from the data-driven approaches that we used to use a lot, like the differential expression analysis. So what we want is to find those genes that maybe are related and are not different in terms of expression, but are important for the disease and for the classification itself, or maybe for a given model to classify a given disease, and are not easily recovered or just with data-driven approach. So that's what we are trying to find, and that's the reason what we are also using the explainability analysis, and yeah, but we are working on it. So
Yeah, great. Thank you.
thank you.